Jackson gave the following rule to create sequences. If x is a term in your sequence, the next term is 1 over 1 minus x. For example, Mary starts her sequence with 3. The next term will be 1 over 1 minus 3, and so on. Fabian starts his sequence with the number 2 and continues using Jackson's rule until the sequence has 2011 terms. What is the second term? So x is going to 1 over 1 minus x, and that's pretty much what we're going to do the whole question. So we started with 2. This is our first term. Our second term would be 1 over 1 minus 2, right? Because it's x is going to 1 over 1 minus x. So this is 1 over 1 minus 2 is negative 1. So that's the second term. And I think that's pretty much the answer to this question right here. The fifth term, okay, so we got to keep going here. Third term, fourth term, fifth term. So again, 1 over 1 minus negative 1 this time. So this is 1/2, correct? And then the fourth term would be 1 over 1 minus 1/2, which would be 1 over 1/2, which is 2. And then we're right back to 2 again. So the fifth term would be negative 1. The sixth term would be 1/2. The seventh term would be 2, and so on. As you can see, it just repeats itself. 2 negative 1/2, 2 negative 1/2, 2 negative 1/2. You guys get the idea. Okay, so the fifth term is this guy right here. So again, that's negative 1. How many of the 2011 terms are equal to 2? Okay, so that's a good question, right? So the 2011, first of all, is this divisible by 3? And the answer is no. It's 670 with a remainder of 1. So every 3 terms, you have a 2. So there's going to be 670 2's. And then there's a remainder of 1. That remainder of 1 basically means that we're back to the beginning of the cycle. And the beginning of the cycle is a 2. So we're going to have to add 1 more. So 671 2's. That will appear in this sequence of 2011 terms. And finally, part D, determine the sum. Okay, well, that's pretty easy because every set of 3 has a sum of 2 plus negative 1 plus 1/2, correct? And we have 670 of those. And then we have that final 2 at the end, the 2011th term, I guess. So that's all this is. So this is 670 times 1.5 plus 2. And that is 1007. Aaliyah has a bucket of coins. Each coin has a 0 on one side and an integer greater than 0 on the other side. She randomly draws 3 coins, tosses them, and calculates a score by adding the 3 numbers that appear. On Monday, Aaliyah draws coins with a 7, 5, and 10. When she tosses them, they show 7, 0, and 10 for a score of 17. What are other scores you could obtain by tossing the same 3 coins? Okay. Well, we have, this is part A, we have a 7, a 5, and a 10. And on the other side, they will have zeros. So there's my zeros. So what are the combinations? Well, for each coin, you have 2 possible choices. And therefore, 2 by 2 by 2, we have 8 possible combinations. So let's list them all. It shouldn't take that long. 0, 0, 0, that's 1. 0, 0, 10. 0, 5, 0. 7, 0, 0. 0, 5, 10. 7, 0, 10. 7, 5, 0. And 7, 5, 10. So these are the 8 possible combinations. So now the sums would be 0, 10, 5, 7, 15, 17, 12, and 22. So these are my sums. And that's pretty much all they're asking in this question. Part B. On Tuesday, Aaliyah draws 3 coins and tosses them 3 times, obtaining scores of 60, 110, and 130. On each of these tosses, exactly one of the coins shows a 0. Determine the maximum possible score that can be obtained by tossing the 3 coins. So we have 60, 110, and 130. So let's label the coins A, B, and C. And exactly, this is an important part of the question, that exactly one of the coins shows 0 on each of the tosses. So on the first toss, we'll make this one be 0, and this will have the values B and C. And that sum is 60. So we'll put that sum there. And then if that's 0, this will be A, this will be C, and that sum, make it 110. And if this is 0, this will be B, and this will be A, and that sum was 130. So we basically have some equations here that we have to solve. And those equations are B plus C is 60. We have A plus C is 110. And we have A plus B is 130. Correct? All right, so, and then we also have, I think that's it. Anything else? Yeah, I think that's it. I was jumping ahead a bit, because what we want to find is A plus B plus C. This is what we want to find, but obviously we need to figure out the numerical values. Okay, so let's just solve this. From this, we get that C is equal to 60 minus B. From this, we get that B, or A rather, is equal to 130 minus B. So then I guess we can substitute both of those into there. So A is 130 minus B, and then C is 60 minus B, and that's equal to 110. Basically just put that in there. So this is going to be, let's see here, 80 is equal to 2B, so therefore B is 40. Okay, great. B is 40, so that means if I sub it back into here, C is 20, and then if I sub it back into here, A is 90. So therefore the maximum value of A, B, and C is 90 plus 40 plus 20, and that is equal to 150. Part C. On Wednesday, Aaliyah draws 1 coin with 25, 1 coin with 50, and a third coin. She tosses these 3 coins and obtains a score of 170. Determine all possible numbers other than 0 that could be on the third coin. All right, so let's set this up in the same way. We have A, B, and C. So 25, 50, and C, the possibilities, 0, 50, and C, 25, 0, and C, or 0, 0, and C. These are the possibilities, right? So if you go back to the question, they tell me that she tosses the 3 coins and obtains a score of 170. Yeah. So, okay. So that basically means that's going to happen when all 3 show the actual number, not 0, because one has 25, one has 50. So in order to get a 170, the third coin had to show its number. It cannot show the 0, because otherwise it wouldn't add up to 170. So that basically means that A plus B plus C is equal to 170. So very quickly we can figure out C's, since we know the values for A and B are given in the question. They are 25 and 50 respectively. So C is 95. So now we can just figure these out using C equal to 95. This sum, I guess I'll just put the sums over here. This sum, well, that's 170. We already know that. This is going to be well, C is 95. This sum will be 145. This sum will be 120. And this sum will be just 95. And what are they asking for in the question again? Well, determine all possible numbers other than 0 that could be on the coin. Okay. I think I know what they're asking for. This is actually kind of misleading. We don't really need that. What they're saying is that in order to get 170, what can C be? So this is just one of the possibilities. Okay, I got it. Okay, so we've done this one. This actually should be over here. This C is 95, that scenario. Okay, so now let's talk about this scenario. If 0 plus 50 plus C is 170, then what happens? Okay, that's going to be 120. Okay, got it. How about if 25 plus 0 plus c is 170? That means c will be 145. Okay. And finally, if this guy, if 0 plus 0 plus c is 170, then c is 170. So the values for c are 95, 120, 145, and 170. Rectangle ABCD. P is a point on BC, so that angle APD is 90. TS is perpendicular to BC with BP equal to PT, as shown. PD intersects TS at Q. R is on CD such that RA passes through Q. Triangle PQA. PA is 20, AQ is 25, QP is 15. Determine the lengths of BP and QT. All right. BP, where's BP? Right here, right? This is BP, and what's the other one? QT. Where's QT? Okay, down here, this one. All right, I think that should be fairly straightforward. Just use Pythagoras. So 16 squared plus BP squared is equal to 20 squared. Correct? So that means BP is 12. I'll let you do the math. It's fairly straightforward. Now QT, I guess we can use which triangle you want to use this time. Well, here's the thing. BP is 12, so that means that PT is 12 since those two are equal. So then we can use Pythagoras again. QT squared plus 12 squared is equal to 15 squared, and therefore when you solve for this, you get QT equal to 9. That takes care of A. B, show that triangles PQT and DQS are similar. That is, the corresponding angles are equal. Okay, PQT. All right, here, we're going to have to label some stuff here. PQT, so I'm going to call this angle alpha, and therefore, since this is 90, this will be 90 minus alpha. And what's the other one? DQS. DQS. Well, by opposite angles, this is also going to be alpha. And then therefore, this is 90 minus alpha. And this is in a right angle. So there you go. Then you can explain it in words that these two triangles have the same angles, which we all obviously showed. And that this one is equal to that one because of opposite angles. And this one is equal to that one because the sum of the angles of a triangle add up to 180. And this angle were already given as 90. So that's pretty much all they want to do there. C, determine the lengths of QS and SD. QS. Where's QS? This is QS. Okay. Well, QS is equal to the entire length, which would be which would basically be ST minus QT. Now, ST from top to bottom is 16, right? And then QT we just figured out was 9, so that's basically going to be 7. So that was easy. SD, okay, SD is a little bit trickier. SD here. I think we're going to have to use similar triangles here. QS, yeah, SD. We're going to have to use similar triangles. The good news is we know what triangles, these ones. So using similar triangles on those two triangles, let's see here, that would mean that QS, which is the 90 alpha side, over SD, which is the 90 minus alpha side, is equivalent to QT over PT. Yeah, using similar triangles. So now if we fill this in, we get QS is 7, SD is what we're trying to figure out, QT we figured out was 9, and PT was 12. So that means SD will be 9 1/3 when you solve that. And then finally show that QR is equal to RD. All right. QR is equal to RD. Okay, so I'd like to keep this diagram in the photo. So we have to show that QR is equal to RD. Okay. All right, well, what I'll do is I think I'm probably going to have to look at similar triangles again, and in particular, those triangles are PQA, which I'll draw over here and avoid making the diagram messy here. So this is PQA, so this is a right angle, and I can use the same symbols, or should I use different symbols? Or does it really matter? Let me think about this. What is the other one here? TQP. Okay, so let me just draw TQP first. TQP. So this is P, Q, and A. And then TQP, that one is kind of like this, right? So this is T, Q, and P, like that. Okay. All right, so I think these two triangles are similar because of the sides, right? Let's label the sides. We have 20, 15, and 25. So this is basically a 3, 4, 5 triangle in terms of the ratio of the sides, right? And then PTQ is very similar, right? If I look at the sides, this is 12. TQ we had figured out was 9, right? And then PQ was 15. So this is also a 3, 4, 5 triangle. So because the sides are the same, the angles will be the same. So that means that if I called this, for example, let's see here. Let me backtrack here before I do this. In TQP, this angle is alpha, right? And that's the TQ side. So that would mean that this would also be alpha. Yeah, I got it. Okay, so that's alpha. Okay, and then of course this would be 90 minus alpha. And this is 90 minus alpha. Okay. All right, so then we can just go back to this diagram and label it in TQP. Well, that's already labeled, so let's label PQA. This is alpha, and this is 90 minus alpha. Okay, well, let me make sure I draw in the right one. Okay, so then by opposite angles, this is alpha, and then by that parallel line rule, that is alpha. So that means that triangle QRD is isosceles, since this angle and this angle are equal. So therefore these two sides are equal. And that means that QR is equal to RD, which is exactly what they wanted us to show, that QR is equal to RD. And that takes care of that. For a positive integer n, the nth triangular number is Tn, which is n times n plus 1 over 2. For example, T3 would be 3 times 3 plus 1 over 2, which is 6. So the third triangular number is 6. There is one positive integer, a, such that T4 at Ta is equal to T10, determine a. All right, so we'll use the standard definition throughout the question. So we have T4 plus Ta is equal to T10. So, using our definition, it's 4 times 5 over 2 plus a times a plus 1 over 2 is equal to 10 times 11 over 2. So solving, we get a times a plus 1 over 2 is equal to, what's that, 55 minus 10, which is 45. So that means a times a plus 1 is equal to 90. And I can do this by inspection. I mean, you can do a quadratic if you want, but I can clearly see that a is equal to 9, because 9 times 10 is equal to 90. So that takes care of part A. Part B. Determine the smallest integer b that's greater than 2011 such that t at b plus 1 minus t at b is equal to t at x for some integer x. All right. So they're saying that b is greater than 2011, okay? And that tb plus 1 minus t at b is equal to t at x. So again, go back to our standard definition up there and plug it in. So we have b plus 1 times b plus 2 all over 2 minus b times b plus 1 all over 2 is equal to x times x plus 1 all over 2. Okay. So that pretty much takes care of that. And not sure where we're going to go. We can get rid of the halves, multiply through by 2. And then let's see, expand this out. And we're going to get b squared plus 3b plus 2 minus b squared minus b is equal to x. Well, I'll just put it as t at x. I'm not sure what this part is going to do to help us, but so let's just well, okay, we can always add it later. I'm just not quite sure what to do with that right now. Okay, let's simplify this side. This side becomes 2b. Well, I guess if I'm going to keep it as t at x, I have to keep that 2 there. All right, well, whatever. 2b plus 2 over 2 is t at x. And then this becomes b plus 1 is equal to t at x. Okay. All right, so I got it down to that. Okay, so what do I do now? Well, b plus 1. Now I can put the official definition. Okay. So b plus 1 is equal to x times x plus 1 over 2. And we got to find... okay. This is... Oh, I understand. This parameter is pretty much the whole question. We've got to find a value for x that makes b greater than 2001, and they want the smallest possible. Okay. So I got it. Okay, so I guess I just have to use trial and error here. And so, for example, if I try x equal to 62 and put it into there, I get b plus 1 is equal to 62 times 63 over 2, right? So that means that b plus 1 is equal to 1953. So that means that b is equal to 1952. Okay, so that came close, but it's not greater than 2011. So let's try x equals 63. That should do the trick. That would make it b plus 1 is equal to 63 times 64 over 2. So that would mean that b plus 1 is equal to 2016. So that means b is equal to 2015. Okay, so that's the smallest. Now, of course, there's going to be other values of b, but they just want the smallest integer b that's greater than 11. So 2015 is your answer to that one. Part C. If t at c plus t at d is equal to t at e, and c plus d plus e is t28, show that cd is equal to 407 plus times c plus d minus 203. Okay. Oh boy. All right, so let's concentrate on what they talk about first. They are telling us that this is true. T at c plus d at d is equal to t at e. And then they tell us that c plus d plus e is equal to t at 28, right? And then they tell me anything else. Let's see here. Oh, we have to show this. All right, so I guess we just have to do some algebraic manipulation to come up with c. They want us to eventually show that CD is equal to 407 times C plus D minus 203. Correct? Okay, so this is all we're given, so let's work with what we are given. All right, so here we go. Okay, so the first thing, of course, is I'm going to figure this out. This is going to be C plus D plus E is 28 times 29 divided by 2 according to the basic definition. So that's going to mean that that is 406. So I guess not much we can do there. I can isolate for one of these. E is equal to 406 minus C plus D, because that looks very similar to this here. So I'll just call that equation 1. Hopefully that will help us. All right, that's about as far as I can go there. Now let's concentrate on that one. That basically is this, C times C plus 1 over 2 plus D times D plus 1 over 2 according to the basic definition. And this is E plus 1 over 2. So multiply through by 2, and you're going to get C times C plus 1 plus D times D plus 1 times E plus 1, like that. Okay, and then I guess this is when I will do the substitution. Yeah. Okay, so let me just keep this for now. I'll expand it eventually. Let me just make that substitution first. So E is this 406 minus C plus D. And then E plus 1, I guess, would be 407 minus this C plus D, like that. Got it? So no tricks so far. And I don't think there will be any tricks. So just basically, now I have to just expand it. Okay, so let's expand this without making any mistakes. C squared plus C, D squared plus D, And then this part, oh boy. We got 406, 407 minus 406. Let me just combine it. 406 and then 407. So what's that? 813? Yeah, 813. C plus D. And then finally, this whole thing, it's going to be a positive. So, and then I'll just do the C plus D expansion. C squared plus 2CD plus D squared. Like that. All right, so that's basically the expansion. And this cancels with this guy. This cancels with this guy. Anything else cancels? Not yet. All right, so all we have here is C plus D. This is 406 times 407. And this is 813 C plus D. And then we just have this 2CD. Okay, this was working out pretty good, I think. All right, where do I go from here? I'm going to put the CD on one side. So just keep the CD here on one side. And then everything else on the other side. So when I combine this guy with this guy, it's going to be 814, I believe. Yeah, 814 C plus D. And then this will be minus. And then I think I can just divide through by 2. So this will be 407 C plus D. And this will be 203 times 407. And this will just be CD. And then at this point, I can factor out a 407. And I get C plus D minus 203 is equal to CD. And I think that's what they wanted, right? Let me see here. They wanted me to show CD is equal to 407 times C plus D minus 203. CD is equal to 407 times C plus D minus 203. There you go. That's what we had to show. And finally, we have D. Determine all triples CDE of positive integers such that TC plus TD is equal to TE, and that C plus D plus E is 28, where C is less than or equal to D is less than or equal to E. So basically, we are just continuing part C. It's exactly the same in terms of what parameters we have to use. And from C, right, we might as well just use, we figured out that CD was equal to 407 times C plus D minus 203, right? We proved it. So that basically means that CD is divisible by 407, according to this. Now 407 is equal to 37 times 11, right? It's when you factor it. So that means that CD is divisible by 37 also. And 37 is a prime. So that means that either C is divisible or D is divisible by 37. So C or D is divisible by 37. So that's sort of an initial preliminary sort of analysis of what C could be, what D could be, that kind of thing. Okay, also from part C, right, we know that C plus D plus E is equal to 406. Remember, we figured that out basically with this. That we figured out 28 times 29 divided by 2. All right. And then we also know, what do we also know? Oh, yeah, this inequality is very helpful. This is going to help us out a lot in this question, this one here. Kind of seems like not that important initially, but it definitely helps. Because if this is true, but then this is also true, that means that D plus E has got to be less than or equal to 406. Because you got to account for the fact that C has to be added. And I think they're positive. Yeah, they're all positive integers. Okay. So I guess now we have to sort of make some conclusions that since D is less than or equal to E, according to that inequality, that means that D plus D, if you look at that, has got to be less than or equal to 406. So that means that D is going to be less than or equal to 203. So this and this those 2 points are what we're going to use to kind of try to figure this out. That d is divisible by 37. It's a multiple of 37. And d is less than 203. So let's try multiples of 37 that are less than 203. So we have 37, we have 74, 111, 148, 185, and the next one is 222, right? But that's not less than 203, so we'll just have to use these guys. All right. So we'll solve for c. In that equation, CD is equal to 407 times C plus D minus 203. So let's first try D equals 185. And when we do, we solve and we get C equals 33. And interestingly, this is the only integer solution. So it kind of saves us some time. And then we solve for E using the same, we can use this one to solve for E. And when you do, you get E equal to 188. So our only triple, CDE, is 33, 185, and 188.